Hello everyone, welcome to our channel, the Digital Institute of Computing Technology. In this presentation, we will have discussion on the topic, the environment of a UNIX process. Consider this simple program to display Hello World. How we compile and run this program. Let's first see how to compile this program. We can use a compiler like GCC. Run the compiler GCC with your source file as input. Hello.c is the source file containing this program. Run GCC with hello.c as input. Now GCC will compile this source file into an object file and from an object file into an exe file. With -o option flag, we can specify the name of the output file. -o hello implies we expect the output file should be named as hello. After successful compilation, the output file named as hello will be created by the GCC compiler. Now we can use the command /hello to run the program and get the output as shown. The output will be hello world. We can check the status of the last program executed using the echo command with $? symbol as the option. In this case, as you can see, the output is 13. Now, what happens when we execute the command /hello? The user interface of the operating system, the shell in case of Linux, will load this exe file into the RAM in some predefined layout. So this is the layout of the C program once it is loaded into the RAM. When the program is running, the CPU fetches one instruction at a time from the RAM and performs operation on the data as per the instructions of the program. The designer of the Unix operating system believed in the idea that files have places and processes have life. Both the file and the process reserves memory space in the system. But additionally, process can perform arithmetic and logical operations and decision making on data. Now coming back to the layout of the C program, these three things are attached to the process at various points of time, that is while compiling, linking, loading, or executing. The C startup routine. The linkage editor will attach this when it is invoked by the C compiler at the time of compilation. Command line arguments are passed to the program during the execution by the user. Environment list passed by the shell when it runs the C program using the exec function. Now let's consider each of these in detail. C startup routine. This is set up by the linkage editor where it is invoked by the C compiler. When a C program is executed by the kernel, one of the exec functions will be used by the C startup routine to call the main function. The executable program file specifies the C startup routine as the starting address of the program. The startup routine takes values from the kernel, the command line arguments, and the environment and sets things up so that the main function is called. The call will look something like this. Exec v is one of the exec functions that could be employed. And to exec v function, we pass arguments like the name of the program, the command line arguments, and the environment list. C startup routine is generally coded in assembly language, but if it were to be coded in C programming language, the call to the main could look like this. Main function invoked with argc and rv, and main returns to exit, which in turn returns to the kernel. It is written in such a way so that if the main function returns, the exit function is called. Now, the C program starts execution with function main. The prototype of the function main is as shown. Here, argc is the number of command line arguments and argv is an array of pointers to the arguments. The main function can have third argument, an environment list, which is similar to an argument list. In this case, the prototype of the main function will look something like this. Now let's see command line arguments. When a program is executed, the process that does the exec can pass command line arguments to the new program. As we saw in the example, execv function is passing three arguments: the name of the program, the command line argument, and the environment. So consider this example. The program in this example echoes all its command line arguments to the standard output device. So this is the program. If we compile this program and execute echo arg, we get the following output: /echo arg with arguments arg1, test, and foo. As you can observe, argv of 0 is the name of the program, that is /echo arg. And arguments 1, 2, and 3 are the arguments that were passed to the program. Argv of 1 is arg1, argv of 2 is test, and argv of 3 is foo. The total number of arguments is 4. So argc is 4 because argc represents the total number of arguments that has been passed, including the name of the program itself. This program runs in a loop and displays all the command line arguments to the output device. Argv of 4 will be null. So the condition in the loop I less than argc could be in fact replaced by argv of I not equal to null. We are guaranteed by both ISOC and POSIX that argv of argc, in this case argc is 4, so argv of 4 will be a null pointer. So argv of 4 or argv of argc can be used as a terminating condition for this loop. As simple as that. Now, environment list. Each program is also passed an environment list, as we saw. The environment list is an array of character pointers, with each pointer containing the address of a null terminated C string of the form name assigned value. It's a name assigned value. It is similar to the argument list. The address of the array of pointers is contained in a global variable called environ. So this is the syntax: extend char ** environ. So environ is a pointer to a character because it points to an array of characters, array of strings in fact. So this is the environment list. So we have 5 strings here in this example: home, path, shell, user, and log. Home has a value /home/scar, path has a value /bin and /usr/bin, shell has a value /bin/bash, user has a value scar, log name has a value sar, and each of this string has been terminated with a /0. Environ is called as the environment pointer. The array of pointers is called as the environment list, and the strings each of these pointer points to are called as environment strings, which are null terminated. Historically, most of the Unix systems have provided a third argument to the main function, that is the address of the environment list. So with third argument in place, the prototype of main will look something like this: int main with arguments argc, argv, and environment list. Argv and environment list envp is an array of pointer to a character, whereas argc is an integer, the number of arguments. Because ISOC specifies that the main function be written with the two arguments, and it says third argument provides no benefit over the global variable environ. POSIX specifies that environ should be used instead of the third argument. The standard suggests that to go through the entire environment, the environ pointer must be used, and to access specific environment variables, use getTNV and putTNV functions instead of environ variable. The prototype of this function is as shown. Need to include the file standardlib.h in order to use these functions. Now let's discuss the various segments in the memory layout of a C program. The text segment. It consists of machine instructions that CPU executes. Usually, the text segment is shareable so that only a single copy needs to be in the memory for frequently executed programs, such as text editors, the compiler, the shells, and so on. Also, the text segment is often read-only to prevent a program from accidentally modifying its instructions. So in data segments, you have category. We have initialized data segment and uninitialized data segment. Initialized data segment, it contains variables that are specifically initialized in the program. The C declaration appearing outside any function causes the declared variable to be stored in the initialized data segment with its initial value. That means any variable outside function, if it is initialized, it will be present in the initialized data segment. Uninitialized data segment, often called as the BSS segment, data in this segment is initialized by the kernel to the arithmetic 0 or null pointers before the program starts executing. The C declaration without any initialization and appearing outside any function causes the declared variable to be stored in uninitialized data segment. Stack. In this segment, automatic variables are stored along with information that is saved each time a function is called. Each time a function is called, the address of where to return and certain information about the caller's environment, such as some of the machine registers, are saved to the stack. The newly called function then allocates room on the stack for its automatic and temporary variables. This is how recursive functions in C can work. Each time a recursive function calls itself, a new stack frame is used. So, one set of variable does not interfere with the variables from another instance of the function. Heap. It is the place where dynamic memory allocation happens. Historically, the heap has been located between uninitialized data segment and the stack. The layout to the right is a logical picture of how a program looks. There is no requirement that a given implementation arranges its memory in this fashion. This diagram only gives us typical arrangement to describe. The stack grows from higher number addresses to the lower number addresses on this particular architecture. The unused virtual address space between the top of the heap and the top of the stack is quite large. Several more segment types exist in A.out, containing symbol table, debugging information, linkage tables for dynamic shared libraries, etc. These additional sections don't get loaded as part of the program's image executed by a process. One point to note here is that the contents of the uninitialized data segment are not stored in the program file on disk because the kernel sets the contents to 0 before the program starts running. The only portion of the program that needs to be saved in the program file are the text segment and the initialized data segment. Now let's consider an example to understand this. In this example, GV is a global variable and will be allocated memory in the initialized data segment. SV is a static variable and will be allocated memory in the initialized data segment. AV is an automatic variable and will be allocated memory in the stack segment. RV is a register variable and will be allocated memory in the CPU register. Hope you liked and enjoyed the presentation. Remain connected with us by subscribing to this channel for latest updates on this channel. Thank you.